Hey there, everyone. My name is Ryan Schul. Welcome to my channel. This is all about data science, machine learning, deep learning, artificial intelligence, and so on and so forth. I talk about a lot of financial topics. I got my MBA in finance a while back, so a lot of my experience and personal interests are in the finance space. But I go beyond that sometimes too. One of my favorite topics is optimization. And another of my favorite topics, I never really discussed this before, so there's no way that you would know about this. But I love environmental things, being environmentally responsible, recycling, reducing my carbon footprint, helping other people to reduce theirs as well. I really like topics like that. So I decided to put together a small series that's going to be about 5 videos all about how to use machine learning for environmental protection. Okay, so today we're going to talk about two of my personal favorite topics is environmental protection and optimization, and we're going to see how to create some optimization models to reduce emissions, reduce costs, okay, and achieve goals of dual goals of lower emissions and money saved. So we'll see how in just a minute to create an objective function, and it's a little bit complicated, but it's not too bad. I'll talk you through it, and hopefully, you'll grasp it and get the concept pretty quickly. Basically, when you create an objective function, there's only one of two things you're trying to do. You're going to maximize something or minimize something. If you're trying to maximize something, usually it's profit, income, cash flow, something like that, something financial. And if you're trying to minimize something, it's going to be costs, okay? In this case, we're going to minimize two things. So fuel emissions or emissions from cars and buses and trains, light rails, things like that. So carbon emissions, we're going to minimize, and costs at the same time. So it's kind of a unique problem. Usually you have to make a compromise with one or the other. You can reduce emissions and it costs more money, or you can increase emissions and it costs less money. Those two scenarios are very common. But today I found a unique way to handle both, right? So we can save the environment and save money as well. So all of the green earthers, I think you'll approve of this. I think we're all in the same camp. There's some people that aren't very earth friendly, and I kind of object to that. I don't like that at all. But let me open your eyes and make you become aware of how you can do two things simultaneously. Okay, I'm not saying that's super easy, but it's not very difficult either, and it's definitely doable. So machine learning is great for helping us understand environmental impacts, how we can handle things more efficiently, more sustainably, what are the overall economic benefits of the decisions that we engage with, right? So I'm going to show you how that works. And again, we're going to use ML in a few different ways. You'll see several applications here: urban and energy planning, renewable energy integration into the problem that we're solving here, industrial process optimization, we'll see an example of that, transportation optimization, and building energy efficiency. Okay, and remember, this is part 1 of 5 in the series about environmental protection. So let's jump into it and see how this works. So I created a pretty simple, straightforward data frame here, and I'm going to share all this code with you. The code goes on and on for several cells here, but don't worry about copying and pasting it. I mean, don't worry about trying to take notes with a pencil and paper. I'm going to share this code with you in the form of an HTML file, so you can copy and paste it, and you don't have to type all this out. Maybe make some mistakes. It'll probably take a couple hours to get everything right. You don't have to do that. Just forget about all that. You can copy, paste, Control A, Control C, Control V, paste it from the HTML file. Okay, so we have the basic data frame here. So this scenario represents a typical medium-sized city, large city, or a small-sized city with the population, population density, average household, so on and so forth. And you'll see all the field names over here. Sometimes they're called columns, in the machine learning world are usually called features. So we are going to analyze these different features and see how we can reduce energy consumption and reduce emissions. Remember, we're trying to do a couple of things here. It's not just one or the other, or this or that. It's going to be this and that. So it's actually two things that we're going to strive to achieve here. So we're going to look at this scenario analysis first. Now, the classic example is stock market. Usually there's a limited number of possible scenarios in a scenario analysis. It can be 2. It has to be, I think, at least 2. I don't think you can have just one scenario. But the best case would be bull market. Most likely would be stable market, and worst case would be a bear market. Okay, this is just one example. This has nothing to do with finance other than economics and budgeting and cost savings. But the classic example of a scenario analysis type of problem is the stock market. Okay, a simulation analysis is when you take a whole bunch of different possible outcomes based on historical actual events, and you add in a volatility metric or a volatility component, and then you forecast this into future and see what the outcome is going to be. So with the scenario analysis, you have a few different types of scenarios. It could be 3, 4, 5. It can be a handful. So it has to be at least 2. With simulation analysis, we're going to have at least 10,000. It could be 100,000. It could be millions or even tens of millions of simulations. A scenario is going to be just a handful. Simulation is going to be a whole bunch of them. That's the difference here, okay? So we're going to convert city size from small, medium, and large into a target variable using categorical coding, right? So if you look over here, we have medium, large, and all the other columns over here are metrics or numerics, right? And that's fine for a machine learning algorithm. A machine doesn't know medium, small, and large. It has no idea what that is. So we have to convert that into a categorical code so we can tell it what is small, medium, and large. Once it becomes a number or some type of metric or numeric value here, like you see here, city size, then we can run this through a machine learning algorithm, right? So the first thing we want to do is make sure that we create city size 1, 2, 3 from small, medium, and large, and make sure all of these other items over here are metrics or numerics, okay? Not really metric, it's more numeric or number, and everything looks to fit the bill there, so I think we can move forward, okay? And we're going to undertake the following type of exercise for the model. We're going to do feature engineering, so we can consider a couple new features based on the existing features. So feature engineering is when you take 1 or 2 or 3 existing features and transform that into a new feature, so you have more features to use in your machine learning model, more to train and test the model, and then to use the model to make predictions. So if you just have a few features, the model can make some predictions. It's probably not going to be too accurate. If you have a dozen features or a couple dozen or even dozens and dozens, that's probably going to help the model, although you can get to a point where you have too many features and the model might get confused. It's called high dimensional data set. So if you have hundreds and hundreds of features, but maybe only 5 or 6 or 7, or maybe a 10 or 12 or whatever, actually have an impact on the target variable, you could have too many features and you have to do a feature reduction exercise like principal component analysis. There's a couple techniques to reduce feature set that has a large number of features into smaller features. But again, you have another problem if you have too few features, right? That would be too sparse, and the machine can't learn from that. So too many is bad, too few is bad. We want to have something right in between. This is kind of the Goldilocks scenario, right? Not too hot, not too cold, not too much, not too little, just something right in between. That's what the machine learning model prefers, right? So let's look at the simulation analysis. Remember, this is a handful, and the stock market example, we had 3. So good market, middle market, and bad market. So we're going to we're going to use a couple different items here, small, medium, and large. This is a scenario, right? And we're going to go ahead and run this code, okay, to create our simulations. Once the simulations have been created, we can go ahead and feed that into the model, right? I'm sorry, we're not even doing a model at this point. Okay, I created this code a couple days ago. I'm just getting warmed up to what I was thinking of 48 hours ago. So, okay, the simulation analysis continues. So we're creating the simulation over here. Now we're going to go ahead and plot all of this on a Folium map. Okay, and that's what this is. So I'll hit Control Enter to refresh the cell. Make sure, I'm sorry, wait, this is a couple of days ago, guys. This is the box plot outcome of the different sizes of cities. So if we look at the small city and zoom in here, we can see the median is the middle number, the max is 9,700, minimum is 8,750. So these are small cities with the max being close to 10,000, the minimum being about 8,750. Medium-sized city ranges from about, where is it right there, 31,000 people to 28,000, right? So that's the typical range for a medium-sized city. And here we have about 140,000 almost from a larger city to 122K on the smaller side. So this shows you the distributions with the interquartile ranges, the high, medium, the low, the midpoint, everything. This is what a box plot shows us, right? So we see how these different sized cities compare to each other, and then what's going to be the emission output from these different sized cities, because this can be totally different based on the number of residents of that city and how they use their own personal cars, maybe bikes that cut down on emissions. That would be great. Maybe a lot of people take the bus or light rail if you have a train system. So there's all kinds of different vehicles, right, to get around the city. So let's go ahead and optimize the emissions. Remember, we're trying to reduce emissions and we're going to try to cut costs at the same time, right? So we have a dual goal. A lot of times it's just one, either cutting costs or cutting emissions. We're going to get crazy here and try to do both simultaneously. And I know this works because I tested it. So I kind of had some insight into how to solve this problem. But it depends on the problem too. Like some of these problems, you'll only have one target variable only costs that you can reduce, and it's going to create more emissions. Sometimes you can reduce emissions, but it's going to create higher costs. In this case, we can do both, right? So this is really like the perfect scenario here. So I am going to create a data frame with emissions, energy consumption, and renewable energy percentage. And by the way, I didn't have this data. I looked around for a while for the data. I didn't find anything, so I'm going to create it so I can do the analysis. So I think this is an interesting problem. I'm going to make the data very realistic, but I don't have actual data for an actual city. Again, I tried to look for it. I didn't find anything. The other day, I looked for data for something relevant to New York City. It took me 4 days, guys, 4 days to find the data. And I finally found it, and I was happy when I found it. That was very specific. So I kind of had to find like that specialized data set. This is a little bit more generic. We're just looking at the size of the city, energy consumption, and renewables. So if you have the data, go ahead and use it in your data frame, plug that in here. I spent some time looking for it. I couldn't find it, kind of gave up and just moved on and created my own data set because I just couldn't find what I was looking for, right? So control enter, I think I just refreshed this. Let me do it one more time. It's not going to hurt. It's only going to help. So we have a few different constraints that we're applying here. These are called bounds. So a bound can be upper bound or lower bound. In between, you call it a ceiling or a floor. These are bounds, limits, constraints, where the optimization engine cannot go beyond that bound or beyond that constraint, either on the upside or the downside. So you're limited to staying within these bounds right here, or these constraints, right? So renewable energy usage, I'm saying it can be a minimum of 35% up to 50%. The first time I did this, I did not have a bound except for renewables, and it went up to 100% renewable immediately. Probably at this point in time, it's early in 2025, we probably don't have access to 100% renewable energy. Maybe in a few select cities, maybe they have that. In New York City, you definitely do not have that. In most cities, you do not have 100% renewable energy at your disposal, right? So you have to pick an upper and a lower threshold, and then set the optimizer, or tell the optimizer, go ahead and pick the optimal solution based on these limits or bounds right here. So I'm saying unoptimized transportation can be 50%, unoptimized energy emissions can be 50%, unoptimized costs can be 50%. So we have this multiplier here, and we have this range. So anything between 35 to 50% for renewables. Again, we want to use some renewables. If it goes down to zero, emissions are going to spike up. We don't want that. If we go beyond 50% renewable, probably not realistic. We probably don't have access to 100% renewable energy. If we did, that would be great. But guys, we probably don't have that. So let's say 50% is the max. So the optimizer is going to work within these thresholds, right? Within these bounds, and it's going to pick the optimal solution for us. So I did the calculations over here, and then printed out the print statements down here. And don't get scared by this. It is a little bit overwhelming, but look at like almost a third of the problem is just print statements, and then the math is kind of straightforward. It comes over here based on these bounds. So the bounds are contained within this list, has square brackets, and all we're doing is multiplying by 0.5 and setting this threshold, saying the optimizer, you have to work within 35 to 50. The highest renewable we can use is 50, and I want to use at least 35 to cut down on emissions. So that's what we're doing here. When I run it, we see the unoptimized transportation emission is 15,519. Optimized is 7,700. So we're winning there. That's better. Unoptimized energy emission. So this is transportation. This is like cars, buses, light rail. Energy emission. So energy to heat people's houses. energy maybe to recharge your car if you use dirty energy like some type of fossil fuel or whatever to charge your car, that is considered dirty energy, and that is going to create emissions when you charge your car. Now, if you're charging your car with 100% renewables, then that's a whole different story, right? I don't think a lot of people actually do that today in 2025. Hopefully, in the future, we'll see a lot more of that. But we still have energy emissions for houses and charging electric cars and transportation emissions. Again, cars, trains, can be anything, planes, automobiles, even scooters, whatever, right? So we're cutting down there. We have 15,000 down to 77, 12,600 down to 6,300. Unoptimized cost, 12,000. Here, the optimized cost is cut in half, almost 6,100. Optimized renewable energy, 50%. So that's the maximum. Remember, that came from over here. So if you think 60%, change that number to 60. If that's your city, I think I live in New York City. It's not even 50%. I'm being generous. It's probably closer to 35%. Might even be less than that. I'd have to see. I did look into this recently, but I forgot some of the details of that. But New York City, I think, uses some nuclear energy too. I think a lot of it's coal and a lot of it is coal and oil. I think they use a little bit of nuclear, and nuclear is actually considered clean. So we have that. And then here's the takeaway here. So transportation emissions change down 50%. So 15.5 to 75, 12 to 61, 12K to 6K. So 50%. And again, this is the optimizer. I'm sure this is coming from this right here. If you change that, that number is going to change. So we're getting the most bang for a buck right here. Renewable energy usage change increase, actually increased 16%. So we probably started with this 35, add 15, and you get up to 50. But the way the optimizer is handling that, it's actually just a little bit more than 15%, right? So that's nice to see. And then we can plot the results here, Control Enter to refresh this, and we'll get a visual representation. I always say a picture is worth 1,000 words. So we're going to go with some stock market colors. I'm a big fan of the stock market. Red is bad, green is good. Here, red is bad, more emissions, right, for transportation, more emissions for energy. Again, for your house, for office buildings, to charge your electric car. If it's dirty, it's still energy emissions. And cost, red is bad, green is good. So here, the cost, with this, all the features implemented from our optimizer, the cost went from 12,000 down to 6,000. Emissions for energy went from 12,000 down to 63, and emissions transportation went from 15 down to 77. Okay, so win-win-win, right? The optimizer is doing exactly what it's supposed to do. It's cutting down on transportation emissions, energy emissions, and overall cost, right? So we have a win-win-win scenario. Kind of hard to find all those things working out to your benefit, but we actually accomplish that right here, right now, today. So congratulations, right? We did this. Mission accomplished. Okay, so what should we note as a takeaway here? The objective function that we have defined aims to minimize emissions and costs simultaneously while maximizing the use of renewable energy. Okay, so that's exactly what we did. We set the problem, we solved it that way. Emissions reduction, so we accomplished that. Energy and transportation impact and costs, so we handled that. And we have the dual benefits of reducing emissions and shifting towards cheaper alternatives like renewable energy. Okay, starting to sound like a broken record here. I think I'm gonna wrap it up in a minute. But yeah, in a nutshell, the optimizer works exactly like it's intended to work. We found solutions where reducing emissions leads to lower energy consumption. And again, it's not always that way, but if you think about it, if you put in a low effort and just a little bit of labor, you can accomplish all of these things, right? So we can do all of these things at the same time. Better energy efficiency and overall cost savings, and decreased negative impact to the environment. So win-win-win, right? We got that. And just in my closing notes here, I have by leveraging predictive modeling and environmental optimization, we can achieve the following: identify key drivers in high energy consumption and emissions, and solve that problem, forecast future environmental impacts based on different usage patterns. Okay. I don't think we actually did that in this case, but that would be maybe a next step to consider, right? Optimize policies and city planning. We did that. Develop smart grids and improve renewable energy adoption or transfer of energy from source to destination. So I don't think we did that either, but that would be another next step that we can undertake, right, if we do more analysis. This was really focused on optimizing emissions and optimizing costs. And that's exactly what we did. So that's pretty much it, guys. Thanks for your time today. I am going to take a copy of this, download it, save as HTML, and upload this HTML file when I upload the video a little bit later today. So you'll have all of this code at your fingertips. You can go in there, copy and paste the code into your own Jupyter notebook, change a couple things, please, by all means, change some of the inputs, change some of the items in this data frame, add a couple new features to this data frame, and then put that into the optimizer and see what kind of impact that has. That's the best way to learn by doing, all hands-on, transactional. You can read this in the book, you can read this on a blog on the internet, but I think if you actually get into the code, make some changes, see what impact that has, you're going to learn a lot more from that type of exercise than just passively reading it, as text posted on the webpage. So that's why I do these videos, to try to help people learn and to just make you more well-rounded and just a better human being. That's it, guys. So, yep, I'm going to wrap it up, and I will see you in the next video. Take care. Bye.